Today we're going to start section 3.4. We're going to look at multiplication of whole numbers. We'll do about half of this section today. Just like when we started with addition and with subtraction, the first thing you're going to do is to define what we mean by multiplication. So for finite sets A and B, if the number of items in set A is A, the number of items in set B is B. If n does not equal 0, then n times A is A plus A plus A plus A, a lot of pluses right here, n times. If n is equal to 0, we say that 0 times A is equal to 0. And then if we multiply the size of these finite sets A times B together, we actually end up getting the number of items in A times the number of items in B. And we've seen that Cartesian product come up before, the number of items in the Cartesian product. So this is the definition of multiplication. All right, so the reason you're in groups is because we're going to take a look at some models of multiplication. So I have four models, for you to take a look at for multiplication. And then after we look at those four models, then you guys in your groups are going to create a question, a type of a question that would fit within that model's perspective. So the first model that we're looking at is the repeated addition model, which looks very much like this first description right here, by the way, right, where I'm repeatedly adding things. So Giselle takes 3 tests every Friday. After 4 Fridays, how many tests has she taken? So in this particular idea, we're repeatedly doing something over and over again. So she's doing 4 Fridays in a row. And this is the same as having 4 times 3. We did it 4 times. That's the n on the previous slide, n. So this is 4. We'll put a 4 there. And of course, that would be 12 tests. Okay, so we're repeatedly doing something over and over and over and over again. We add it together that many times, we end up getting, in this case, 12 tests. So that's one model, repeated addition. The second model is an array model. So an array model is used for sets, whereas you'll see in a moment we're going to use an area model, very similar, but for measurement. Minhu is baking cookies. He's able to place the dough 3 cookies wide and 6 cookies long in his pan. How many cookies will his pan hold? This isn't repeated addition. He didn't bake 3 cookies today and bake 3 cookies tomorrow and bake 3 cookies the next day, right? He's doing it all, but he's doing it in a model that you can see. Think of a cupcake tin, or this is cookies, but he's baking them in an array model. And there's lots of things that we use on a regular basis that use array perspectives. So you'll have a chance to explore some of those in a moment. So we're going to do 3 wide, just because of my space. There's 3. And then I need to do 6 long. So a picture looks something like that. And we see that we have 3 in one dimension. We have that 6 in the other dimension. And 3 times 6 would be my 18 cookies. Okay, so remember we talked about back in section, at least in the section on addition, I think. We may have done it a little bit in the section on subtraction as well. This idea of things that can be partitioned and things that can't. So cookies are whole objects, right? But if you take a look at the next one, we're talking about a measurement of something, right? So while you could talk about a garden from either perspective, if you're talking about a garden from a set perspective, you're looking at the individual flowers or plants in the garden. But if you're looking at the garden from the area's perspective, right, length times width, like dimensionally speaking, you're looking at a measurement model. So Alexis is planting a garden. She has a space that is 5 feet wide and 7 feet long. How much area does she have in which to plant? So your picture does not look like individual, shapes, right? It looks like a rectangle. In a very real sense, we're going to be drawing a rectangle on this one. In my rectangle, is that it's 5 feet in one direction and it's 7 feet in the other direction. And if you wanted to grid it through, like you could make grid marks in here and that would be good too. I mean, you could see it from a grid's perspective. My grid's not going to be perfect, but you can pretend that it is. Okay, it could have been a lot worse. And I have my 5 times my 7 for my 35. We are doing feet times feet, right? Our garden was 5 feet wide, 7 feet long, so this is square feet. When we multiply feet times feet, we get feet squared or square feet. So if you were drawing this picture, I don't necessarily need you to draw in the grid, but it might be helpful for a child if they're seeing this the first time to see why it's 7 times 5, because you can count all the little boxes if you do that. Okay, so this is model number 3. The last model is a Cartesian product model. Kind of shouldn't be a surprise that we have this model because our definition talked about things from a Cartesian product perspective over here, right? The last one, where we multiplied inside of the parentheses with the sets themselves. So our Cartesian product is a way of choosing options. So for example, Unique is at a pizza place and she can choose from 2 types of crust, thin or original, and 3 types of toppings, pepperoni, sausage, and ham. How many different types of pizza could Unique choose? So if we're thinking about this, and I don't know that I have enough space for this, I apologize. We'll use another one at the end. Just throw it in the over here. So for this one, get lighter, gray. So the first piece that she has to choose from, so I'm going to think about this kind of like a tree diagram for those of you who've had proportional statistical reasoning. Oh, it's not hard, I promise. We're not putting probabilities anywhere on the thing. So she has an option of thin, or what was the other one? Was it thick or was it medium? What was this? Original. Thin or original crust. And then she had 3 different toppings. What were her topping options?
Pepperoni, sausage.
Okay, so we have pepperoni, sausage, and ham. So she could have a thin pepperoni, a thin sausage, a thin ham, or she can have an original pepperoni, an original sausage, and an original ham. So if you count at the very end, that shows all my different options over here. I have 1, 2, 3, 4, 5. I have 6 different types of pizza she could have. So you're breaking it down into choices is all you're doing. Any questions on that?
Would it have worked to just do our 2 types of crust types or 3 toppings?
So it works that way, but this is supposed to be verifying or showing why it works that way. So yes, it is 2 times 3 because we have 2 of these options and 3 of these options and we're multiplying it together. And so we're trying to create a visual that shows that. This isn't the only visual that would show that, but it works pretty nicely to show options of things that are happening. Okay, so what you guys are going to do next is you're going to, in your group, create a word problem. You don't need to solve it. You don't need to draw the pictures. Just a word problem that fits into these categories. So I haven't mentioned this before, but the reason that we're doing this is because if you can identify as a child is working that every time they miss a subtraction problem, it's because it's a missing add-ins problem, that helps you a long way into going and figure out what it is you need to do to help them. If every time they miss a multiplication problem, it's because they're choosing options here in this Cartesian product, then you're able to talk specifically about what it is about that structure, that problem, that means that it's a multiplication problem. Because if you keep giving them examples of ones that they know how to do, you're just going to frustrate the situation. Does that make sense? So there are these different sort of broad perspectives of the ways that multiplication are coming about, and that's what we're examining today. So you're going to look at 4 different types of problems: repeated addition, array, area, and Cartesian product, and you're creating a word problem to go with them. Okay? So you guys can do that next. All right, I need a volunteer. What did you come up with for repeated addition? Somebody?
Show us 3 cups of coffee every day. How many cups does he drink in a week?
Oh, that's a very good example. People do that, right? All right, did you guys hear? Yes. 3 cups of coffee every day. How many in a week? All right, one more example of repeated addition. Somebody else give me your example. Karis, you're smiling at me. What you have?
Sam gets 4 go-go squeezes every Monday. After 4 Mondays, how many go-go squeezes has he had?
All right, so he's getting a particular kind of a product every week, just like the day one for her. Good. All right, how about array model, a group that hasn't gone? Hallie?
The event center is holding an event for a birthday party. The center is able to hold 5 rows of 10 chairs. How many chairs can the center hold?
Excellent. So rows of chairs is a good example of an array model. Very good. What else do we have? Somebody else who has one of your groups that haven't gone.
We said Ruth is planting flowers in her flower bed. The flower bed is able to fit 3 flowers wide and 7 flowers long. How many flowers can fit in a flower bed?
Perfect. So flower bed arrangement. So it feels kind of like it's going to be an area model, but because it's doing flowers and not the space, it's an array model. Very good. So some other things that might come up with array that you might think of, or maybe you didn't think of, is like soda cans, right? Like in a 12-pack, 24-pack, things like that. Those are in arrays. I heard the middle group talking about cupcakes. I have cupcake pans that are in array models. Toilet paper rolls. Those are in array models. So there's lots of objects that are in array models, so they're good examples. How about an area one? So in the middle, Jordan, what do you got?
John buried his money in his backyard and can't remember where it is. His yard is 20 feet wide and 25 feet long. He wants to dig a hole in each square foot till he finds it. How many holes will he have to dig to find the area?
Cool. All right, so you could also just shorten it a little bit if you wanted to. Instead of part about the digging the holes, it's just how much space does he have to search from or something like that. And we'd still have the same idea. Yeah. So I know everybody's gone at least once now, so you get to volunteer. Who wants to give me another example of their area model? Somebody does.
We said Shawnee is building a trampoline park. They have a warehouse that is 200 feet wide and 570 feet long. How much area do they have to fit trampolines?
Awesome. Are they? Can we have a trampoline
I
park?
wish.
That'd be amazing. We should have one. All right, how about Cartesian product? What'd you guys come up with? Somebody, I know everybody's gone at least once now, so Hallie.
Gregory is making ice cream sundaes for his friends. He has chocolate and vanilla ice cream along with a choice of 3 toppings, sprinkles, M&Ms, and nuts. If each person can only have 1 flavor and 1 topping, how many options of sundaes do they have to choose from?
Fabulous. You're not the only group that was talking ice cream. So, yeah, awesome. So we have different options of sundaes. One more Cartesian product. Okay.
We say Gracie brings 4 tops, 2 bottoms on vacay. How many outfits can she create with her options?
Yeah, different numbers of outfits. Very good. All right, cool. So we're going to then move into looking at some of the properties for whole number multiplication. We kind of struck out when we did subtraction. If you remember, nothing worked. But if you remember, when we did addition, everything worked. So we kind of have seen both sides of that. We're looking at multiplication in this section, and we have this idea of closure again. So you guys did quite a bit now with closure in your homework and your group work. Closure is the idea of taking a set. In this case, we're talking about the whole numbers, and an operation. And in this case, we're talking about multiplication. And when we take the whole numbers and we multiply them together, we get other whole numbers. That always works. So you multiply a whole number by another whole number, you get another whole number. The commutative property also holds. So when we multiply 2 numbers, 5 times 3, it's the same as multiplying 3 times 5. Again, it's much like when we did addition. This is helpful to kids when they're learning their multiplication facts. Man, I'm so glad it works this way, right? They have to memorize half the number of facts if it didn't work this way. Because once we get up to, like the 9's multiplications, they've learned everything except for 9 times 9. This is for single digits anyway. This works very nicely. So we have the commutative property that says we can multiply in any order. We also have the associative property. The associative property says that I can regroup. So you notice the A, the B, the C, they're all multiplied together. The difference has to do with what you multiply first. So on the left-hand side, I'm first multiplying A and B, and then taking that product times C. On the right side, I'm multiplying B and C, and then I'm taking the result of that and I'm multiplying it by A. and you'll always get the same value. And the reason that that's useful is because sometimes it's easier to multiply two values together than something else. There's an order that actually makes it work better, and we'll see that happen when we get to strategies at the end of this section, which will be next class period. We have an identity property, so it would be probably a good idea for you to write in the words that this is the multiplicative identity. Because if I were to ask you to identify something that has an identity property, you need to specify if it's multiplicative or if it's addition, because the identity elements are different. The identity element for addition was 0. The multiplicative identity is the number 1. Because you can take the number 1 and you can multiply it in either order by any number, and it won't change the number you're multiplying by. So a times 1 is the same as 1 times a is the same as a. It's a very useful fact when we are working with fractions later on. I know that's not this semester in this class, but when chapter 6 happens and you multiply the numerator and the denominator by the same value, you're multiplying by 1. You need that to work. So it's a very useful property. And then there's 2 more. You have the multiplication property of 0. So 0 is the unique whole number where when we multiply any number by it, it zeroes it out. Right? A times 0 or 0 times a both yield 0. And the distributive property combines 2 operations. It combines the operation of multiplication, right? This parenthesis right here is indicating that I'm multiplying, with either addition or subtraction on the inside. So when I have the multiplication of a times b plus or minus c, I'm distributing the a through, so I end up with ab. I end up with AC, and whatever the sign was between the B and the C to start with, it stays the same. So what we're going to end with today is identifying some properties at play. So we have 6, I think there's 6 of them that we're going to take a look at. And they're wanting us to identify which whole number property is coming into play in the problem that we're looking at. So what property do you see present on part A? Yeah, the 0 one over here. It said multiplication property of 0. Oh, let me use black. How about the second one? Somebody said it. It's commutative. So it's real tempting to see parentheses and think you're doing something with associative. But what's happening is what's inside changes locations, right? I didn't change the values that are inside. I just swapped the orders. The 3 times 4 became 4 times 3. So this is actually the commutative property. How about C? That one is associative, right? The parentheses actually shifted. They were around 3 times 4 on the left. They're around 7 times 3 on the right. So this is the associative property. Be careful on abbreviation with that. How about D? Oh, it's close. Identity. Yeah, specifically because there's a number 1. So if we wanted this one to be written and to think that it was the distributive property, we would want it to be written, well, actually, that's not true. I was about to say something that's not true. It doesn't have addition on the inside, so it wouldn't be distributive. My apologies. Yeah, this one is the multiplicative identity. And do make sure you're writing multiplicative.
Do we have to add that term to the other ones, or just?
We actually had it when we did it before. But yes, if you were using this with the stuff in section 3.2 where we had the additive identity, we need to say additive identity. Yes.
For commutative and associative?
Oh, so they work the same way. So if you say commutative property of multiplication, that's fine because it works the same. I mean, the operation is multiplication that we're using, but it works exactly the same way. The reason that it's important when we're talking about identity specifically is because the number is different. 0 or 1, and that's why it matters for this one specifically. But if you want to be more specific, yeah, it is the commutative property of multiplication, the associative property of multiplication. How about E? That one is distributive because I've got addition inside of parentheses, I've got the multiplication on the outside, and we see our, in this case, 5 being distributed through. It's on the back end, but that's okay. That's not a problem. This is the distributive property. Be careful on F. What do you see happening on F? Emily? It's not associative. It's a good guess. It is distributive. Grace, what's distributing? Can you tell?
The 1 plus 2 is
Mhm.
distributing to the 3.
Yeah, it's the 1 plus 2 that's distributing to the 3 and to the 4. I didn't draw that well. So the 1 plus 2 multiplies by 3. The 1 plus 2 multiplies by 4. So this is another example of the distributive property. Okay, any questions on those? All right, we will pick back up with JJ next time.